Hey there, this is a screencast. I'm calling it Confidence Intervals Large Sample. In this screencast, I'm going to work through an example of computing a confidence interval for an expected value. And then I'm going to do the reverse, give you a confidence interval, and we're going to show you how. Hey, this is a screencast. I'm calling Confidence Intervals Large Sample. In the screencast, I'm going to do two examples. One where we'll start with a level of confidence and compute a confidence interval. And the other example, we'll start with a confidence interval and ask to figure out what level of confidence that represents. And each example will have some more data that we'll work from. Let's go to it. So here's example one. So a company manufactures widgets whose weights have to meet a certain condition. And a quality control engineer takes a sample of 40 widgets and calculates the mean weight of the sample as 16 grams, and its standard deviation is 0.9 grams. And our job here is going to be to find a 90% confidence interval for the expected weight of a widget based on that sample. So let's do it. So we know a confidence interval is going to look like, an interval notation, like some number a, comma, some number b. And what these numbers are going to be, right, is our sample mean plus or minus r, where r is some radius. Of course, it's a positive number. And notice the sample mean is right in the middle. We want a 90% confidence interval. So we need to calculate our alpha. So 90% confidence means 90 and alpha are related in this way. So if you solve for alpha, you get 0.1. And now we want to take that alpha over 2 is 0.05. And this is going to be the basis for our calculation. So specifically, our confidence interval, this radius, looks like this. Our confidence interval is the sample mean plus this z alpha over 2 times our sample standard deviation. And this is what we're going to want to compute. Just a reminder what this is. So the z stands for a z-score, where capital Z is our standard normal distribution. So this z-score here is the z value at which our probability here equals alpha over 2. Geometrically, what's happening is if here's the z distribution and it's got mean 0, what we're doing is for the confidence interval, we want to know this region of the distribution that has 95% of the area. And this is going to be centered at the mean. That means 10% of the area is going to be in each of the tails. So each of the tails are going to have 5% of the area. Because the distribution is symmetric, there's going to be exactly 5% in both tails. So it's this cutoff here on the x-axis that gives us this z alpha over 2 value, because the probability that our standard normal gives us a value that's less than that cutoff is 5%. So we want to know where that cutoff is, right? And this is like a quartile. This is a quartile. R would call this a quartile. And in fact, it's the 5% percentile, to be precise. So that's what we're trying to find with this alpha over 2, the alpha over 2 percentile. All right, let's keep working. So our oops, I made a mistake. The standard deviation here is the standard deviation of the sample mean, not of the weights themselves. So I have to put that square root of n down there. So our confidence intervals look like this. So let's fill in what we know. Well, we know our alpha over 2 is 0.05. We know our sample standard deviation was 0.9. We know our sample size was 40, so we're dividing by square root of 40. We know x bar is 16. All right, so what's this z.05? Well, there's a bunch of ways that we can calculate that. We could go into the textbook and we could use the z table, but let's use R. So we're going to use the Q norm, so that's the quartile for the normal distribution, and we're doing the standard normal, and so it's the standard. It's got mean 0, right? The mean goes here, and the standard deviation goes there. So 0 and 1, that's for the standard normal. So that's what we want to calculate. You plug that into R, and you'll get the number negative 1.644854. And then the last number, oops, works out to that. I think that's a 0. So we're getting a negative number, and it feels a little weird to have that negative number here and that plus or minus, but just play along. It doesn't change the fact this becomes a minus or plus. It doesn't change the fact that we'll get the endpoints. But why should we get a minus sign there? Well, let's go back and look at this picture. For the standard normal, we're looking for this quartile, the 5% quartile, the 5 percentile. The middle of the distribution, that's the mean, that's 0. So if we're to the left of 0, we're definitely going to have a negative number. So we expect that negative number. So I feel okay about that. All right, let's take one step further. This is 16.0 plus or minus 0.234066828. And this gives the interval 15.77, 16.23. That's our confidence interval, our 90% confidence interval. So we might write something like that. So we expect the weight of a widget to be 16.0 plus or minus 0.234 grams. That's one way to express our confidence interval. Okay, good. So let's flip this around. Let's do another example here. So let me write the statement of the problem we'll do. So the quality controls engineer's colleague reports a confidence interval for the expected weight of a widget to be this. She took a sample of size 40 and calculated a confidence interval using that data. So the sample size should have been the same, and the standard deviation of her sample was 1.1 grams. What was the sample mean of her sample? And what is the level of confidence of this interval? That's what we want to answer. All right, so let's remember a couple things about confidence intervals. Confidence intervals look like x bar plus or minus z alpha over 2 times s over the square root of n. So these are what the endpoints look like. Notice that the sample mean, right? What does the sample mean? The sample mean's right there. It's the midpoint. So the sample mean should be the midpoint of this interval. So the sample mean should be 1/2 at 15.7506 plus 16.2504. And you work that out and you get 16.0. That should be the sample mean according to the confidence interval. All right? So to the next question. What was the level of confidence? So we need to find out this alpha. Right? So we have our level of confidence, whatever that is 100 times 1 minus alpha. Well, how do we find alpha? Well, remember, our confidence interval looks like this. So this number right here is the radius. So let's look at this. How do we find the radius of this interval? Well, it's the difference between the center and one of the endpoints. And we figured out the center was 16. So you can just kind of look here. Look, compare 16 midpoint to that. It looks like we can just see that the radius is 0.2504. Okay. So this shows 0.2504 is this percentile times our sample standard deviation, which we were told is 1.1, over the sample size under the square root. So I can multiply both sides. I can solve for this percentile, and I get 0.2504 times the square root of 40 over 1.1. And you do this, and you get approximately 1.437399. All right, so now how do we find alpha from this? Well, it's good to remember what these z-scores are. Right? These are percentiles. So what does this tell us? This tells us that if I have the standard normal, so this is at 0, I know that actually what I need to do is, remember we talked about that minus sign. I need to put the minus sign in there. Okay, so the z alpha over 2 here is the place where the area of the tail to the left of that z-score is alpha over 2. And what we have just computed is that this is negative 1.437399. All right, so how can I calculate the area to the left of this place? Well, this is just the probability that z is less than negative 1.437399. And we can calculate that. Pull up R. What's the probability, if we're in a standard normal, of us getting a value that's less than or equal to that? Well, that's what this pnorm command gives us. And it tells us the probability is 0.075302333. So that tells us alpha over 2 is 0.075302333. So So multiply both sides by alpha, and I get 0.1506047. So 100 times 1 minus alpha, our confidence is 79.03053%, or about 80%. So that's the confidence level that goes with this interval. Okay, 2 examples help you understand how confidence intervals work.